Turning up. How's the lighting? That's about right? We're all good? Okay, let's get underway. So, I took this image just with my standard iPhone out of my pocket about 9 p.m. Saturday the 11th of May, Gulf Harbour looking back to Auckland there, and I'm sure you know all what you're looking at there, the Aurora Australis, or also known as the Southern Lights. Many of you also saw all that out there. Yeah, absolutely. It's pretty exciting stuff, isn't it, to get it so far north. And if someone said to you, okay, you're part of the Astronomical Society, what are we looking at here? You know, a reasonable answer would be, charged particles from the sun interacting with molecules in the Earth's upper atmosphere, causing them to glow. Isn't it nice? You know, that's pretty reasonable. Most people go, okay, I get that. But then you might ask yourself, okay, let's learn a bit more about this. Why? How did those charged particles get like they are? What made them come from the sun to Earth? How are they interacting with Earth's atmosphere and the molecules? How are they giving out light? And those are some of the questions you might be asking yourself, and where are the best places to see it, and so on. And that's why tonight's talk is called The Sun and the Southern Lights. What's going on? Because I thought it's very topical. As you'll find out later, we could be in for some more this week if the clouds behave themselves. And you're going to learn today, we're going to be talking about the internal structure of the sun. That is very relevant to this. You're going to learn about radiative and convective zones. You're going to learn about magnetic lines in the sun. We're going to talk about solar flares. We'll talk about coronal mass ejections. We'll talk about clouds of charged particles entering the sun, the Earth's atmosphere, going down magnetic lines and causing oxygen and nitrogen to fluoresce. And this is the sort of stuff that we're going to be talking about tonight. So I've split it into these 3 chapters. The key two, of course, the sun and the solar activity, the Earth's magnetic fields, and then we'll sum up. So the sun and the solar activity, this is very relevant to the talk. It's not just talking about what goes on inside the sun is very, very relevant. So next time, at the end of this talk, next time you see an image like that in an aurora, you'll be thinking this. That's what you'll be thinking next time. That's the goal anyway. So the sun is a G2V star. What does that mean? So the star part means it's self-illuminating. It's a spherical ball made up of extremely hot gas known as plasma, and it's fueled by nuclear fusion at its core. The V part is Roman numeral for 5. That tells an astronomer that the sun is on the main sequence, implying that at its core it's nuclear fusion processes hydrogen into helium, and the G2 part just tells us that the surface temperature is about 5,800 degrees. So that's the sun in a nutshell. Okay, now let's have a look at the sort of insides of the sun and the external. So it's got 3 inner zones and 3 outer zones. And this is not just academic. This stuff is relevant to what we see when we look up at auroras. So starting off with the core of the sun, right in the centre there. Because of gravity, the downward force, the temperatures in the core of the sun, about 15 million degrees. And it's hot enough to fuse hydrogen into helium. 600 million tonnes per second of hydrogen gets burnt into helium at the core of the sun. The core extends out to about 1/4 of the radius of the sun, very, very roughly. It's an easy figure to remember. And that nuclear fusion produces high-energy gamma-ray photons and some little particles called solar neutrinos. That's a whole entire talk. But just these high-energy gamma-ray photons, all this energy coming from the core, this is what drives the sun, what fuels it, what drives all the forces that go on. Everything we talk about is originating from here. So moving out to the next zone is known as the radiative zone. And that's roughly from about 1/4, it takes roughly about half the radius of the sun out until about the outer quarter. That's sort of a good estimate. And it's called the radiative zone because the energy, in particular those gamma ray photons, go by a radiative fusion process of working their way through that zone into the next zone. And it's by a constant thing of being admitted by particles, then readmitted, absorbed by particles, admitted, absorption, readmitted, and they just go on and on and on, to the point of one photon takes up to about 170,000 years to traverse that distance there. That's the long part of it getting through. Now, here is the important part. If this is one of the key messages you must take home tonight, is that this here, it's not hot enough or dense enough for nuclear fusion, but it's still very, very dense, this whole area, because of the compression, whereby this whole region here rotates as a uniform solid. Much like the Earth. You know, when the Earth rotates, it rotates uniformly. No matter where you are on the Earth, it's all rotating at the same rate in a uniform way as a solid. That's a really important thing just to keep in mind as we talk more about the Sun. Because the next stage is the convective zone, where your photons, much lower energy now, they've lost energy as they've worked their way up over the last 170,000 years. And this works by what we call convection cells. And that's where you get these large regions or packets of plasma particles, if you will. The heat warms up from below, warms the little packets up. When something warms up and heats up, what does it do? It expands, which means it gets less dense. What does it do if it's less dense? It starts rising. Rises to the surface of the Sun, gets rid of the heat, so it cools down. When something gets cool, what does it do? It contracts. That means it gets denser, it means it gets heavier, so it starts falling back down again. And the cycle goes on and on. Common example, every morning you do that with you make your coffee, with you boil up your electric jug. That's convection, how it boils away. So this outer zone here allows energy transport by these convection cells. And it takes about 10 days for the photons then or the heat, if you will, the heat to come up here, and then photons and optical wavelengths gets released from the surface of the Sun and take about 8 minutes to get to Earth. So that's how the energy gets transversed through the Sun. Here's the other thing, one of the key things to keep in your mind throughout this whole talk, is that convection zone, because it's much less dense sufficient for a convection to occur, that it behaves like a fluid. Instead of a solid, it behaves like a fluid, so as it rotates. And a quick spoiler alert coming up. If you want to find out what happens later on, you can close your ears, but otherwise I'm going to show you later how different latitudes experiences different rotation rates. At the rotation of the equatorial latitudes of the Sun, it only takes about 25 days for something to go right around the Sun. Up here, you're talking up to 35 days. So that's what we call differential rotation, because that's rotating as a fluid. We'll talk about that later. Spoiler alert over now. You can focus again. That's the relevance. So that's really, really important how the Sun works, is that inner radiative zone is a solid, rotates uniformly. The outer convection zone, less dense, rotates as a fluid. So the end results, as we've talked about, these gamma ray photons work their way up to the surface. They take about 8 minutes to get to the Earth from there, but they take up to about 170,000 years to get their way from the core through to the convection zone. So you might think, well, how do they know all this sort of stuff? Well, it's the same way that they know the interiors of the Earth, is through seismology. That in these convection zone here, there's a lot of acoustic pressure waves going on with that whole convection movement, and those acoustic pressure waves reverberate through the solar interior, and you actually see pulsations on the outside of the Sun, which they can observe and measure. And what the science is called helioseismology, just like seismology on Earth. You analyse various vibrational energy in different parts, and you can work out the interior and how the densities, rough densities, and how far and deep things go. So those are the three relevant interior zones of the Sun, relevant to why we get auroras. Also relevant is the three atmospheric zones of the Sun. And the first one is the photosphere. It's the surface of the Sun, essentially. It's only about 400 kilometres thick, and it's very opaque, and it's where those photons of light and optical wavelengths are first released. So the temperature, as I mentioned earlier on, is 5,800 degrees. Its surface looks quite granular. When you see photographs or images or diagrams of the Sun, you see all these little granules. That's what you're looking at, the surface of the Sun. And the key point out of this is we're going to be talking a lot about sunspots. And it's the photosphere is the site of sunspots, which are really, really relevant to our talk today. Then there's the chromosphere, which is this layer here. It's a little bit sort of a diffuse sort of layer. It's roughly about 4,000 kilometres. And it has these what they call spicules, which are hot jets of plasma shooting up. Got a picture of them here. Look at that. They look like sort of fairy, don't they? Like a carpet almost. But these are spicules. The millions of jets of plasma called spicules that propelled upwards and outwards off the surface of the sun. They're not small. They look small here, but they're not. The diameter, average diameter is about 300 kilometres. So, you know, every one of those, the thickness is about 300 kilometres. They have upward speeds of about 100 kilometres per second. So that plasma has been shot up at high speeds. They last for about 15 minutes. And they get to altitudes, they get up to about 10,000 kilometres. So what is driving all that? Once again, ultimately, it's that nuclear fusion, that heat transfer from the core. I can't emphasise it enough. That's driving all of this. The energy is coming up. And once again, you're getting these spicules of hot plasmas being shot up into the upper atmosphere of the sun. Now, the next part is the corona. The corona is very ill-defined. Temperatures, in other words, the amount of kinetic energy, things are moving around up there, up to 2 million degrees. So things are flying around at huge velocities up there. And the importance of the corona is twofold. One is it's the site of these three activities here we're going to be talking about: solar prominences, flares, and coronal mass ejections, all very, very relevant for aurora. This here is what you're looking at with a total solar eclipse. You're looking at all the corona extending out here. That goes out for millions of kilometres. And that's actually what you see with your own eyes, just looking through a very simple telescope or binoculars in a total solar eclipse without any fancy filters on. That's what you're looking at. And all the crimson around here, that's chromosphere all around here with some solar prominences we'll look at later. But the other thing, the second thing, the corona is very important, and all these spicules and stuff. So I've explained the heat's coming up and you're getting all these spicules of hot plasma getting shot up to the atmosphere. The atmosphere is very tenuous, it's very diffuse and ill-defined. It extends for millions of kilometres. So it's only natural that you're just going to get an outflow, constant little low flux outflow of particles going on all the time into space. And that forms what we call the solar wind. It's just a steady stream of charged particles from the corona. They're usually just under they're in the hundreds of kilometres per second. 4 to 6 billion tonnes per hour, just constantly coming out of the sun, just spreading out in all directions. And it's predominantly electrons and protons and alpha particles, which are also the nuclei of helium atoms. So that's the solar wind. So just wrapping up that little section there, you've got your three inner zones, your core, your radiative zone, and convection. Remember, the radiative zone behaves as a solid, rotates uniformly. The convection zone behaves as a fluid because it's less dense. And then you get the surface, the photosphere, the chromosphere with all these spicules of hot plasma shooting up into the corona. Okay, so we're now going to move on. We're going to talk about the sun's magnetic activity and the cycles of the sun, the solar cycles. And the question we should be asking ourselves at this point is, what creates magnetic field lines and how do they cause solar activity and ultimately the beautiful aurora that we see? And the answer is two things we're going to talk about: differential rotation, which I've already given you a spoiler alert on, and the tachocline layer. We're going to look at these two things now. Okay, so here is that differential rotation we talked about. This is a diagram. It's easier to see things in diagram form. So here's the equator of the sun, North Pole, South Pole. And you'll see here how the plasma, the convection and the photosphere behaving like a fluid. It rotates about every 25 days around this latitude. And the higher latitudes you go in either direction, it slows down. It's actually rotating a slower rate. So it takes 26 days here, it takes 28 days to do a complete circuit of the sun here, 31 days and 35 days, and so on. So you can see that depending on your latitude defines how fast that plasma is rotating around. And that's called differential rotation. That's what it is.
What's the rotation period of the solid bit in the middle?
Okay, we're about to come to that. Actually, it's. I think you'll find that'll be closer to the 25. We're actually going to come to that. I've got a graph. So the tachocline layer. So here's your radiative zone. Here's your convection zone up here, and right in between here, that's the tachocline layer. Remember, here's the radiative zone, uniform rotation, the convective layer, differential rotation like a fluid. And here you go here. This just illustrates it quite nicely. So here's a graph here. You've got your rotational velocity, and they've put it here, an omega over 2 pi. I actually can get that figure for you, Martin. I'll get that figure for you from Plucky because I've got it on here. But you'll see it's all uniform. The rotational rate of the, you can actually work it out from here. Here's the rotational rate in the radiative zone. Here's your latitude going up here, and here's your solar radius going out here. Just very crudely, there's your radiative zone, here's your convective zone with your differential rotation, and in between here is called the tachocline layer. So you'll see here, Martin, you'll see it's probably in between. It's an average, roughly. Let's just call it that. Does that answer your question, sort of roughly? Yeah, you can see it there, it's average. Okay, so that illustrates the point of this tachocline layer. The importance of the tachocline layer is that you've got that radiative zone going around uniform, but overlying at different latitudes, you've got charged particles going over the top of charged particles at all different velocities. And it creates, not only does it create shear forces, but different shear forces as well. So we looked from that last graph, you could see there that at, say, latitudes of, let's actually start at the equator, it's going a lot faster than the radiative zone, and at the pole, it's going a lot slower at the radiative zone. So at all different latitudes, you've got different velocities in comparison with that radiative zone velocity. And that creates these shearing forces. And what happens when you get forces going on, charged particles moving against one another, you start getting electrical currents. When you start getting electrical currents moved with extra forces added on like this, you start getting magnetic field lines. And you start getting horizontal magnetic field lines, like, rather vertical magnetic field lines like you see here. And I've got the south pole here, north up here, and you've got these lovely vertical magnetic lines, a dipole magnet effect. Now, here's the thing. Add in your differential rotation, and suddenly these nice vertical magnetic field lines start getting twisted and distorted at different rates. Look at the equatorial, they're getting stretched more because you've got faster velocity, but less up here. And as the sun rotates around, with every rotation, they start getting more and more twisted and distorted, these magnetic field lines. What happens next is interesting. It's like a rubber band. As you start getting loops of these magnetic field lines start springing up perpendicular and start poking up through the surface of the photosphere. And a really good analogy here, if you've had a real thick rubber band and you just get a thick rubber band and just wind it and maybe get someone else at the other end of it and just keep winding it and winding it up the tension and the stress within the rubber band. What happens? You'll see little loops perpendicular start flicking upwards. You get 2 or 3 of them per rubber band, just like they've shown here. That's exactly what happens. And the distortion, the differing distortion and stress of these magnetic field lines, you start getting loops punching up through the photosphere. And that's what we call solar activity. And here it is here. I'm going to show you shortly. This occurs with 11-year cycles, and it's responsible for sunspots, which we'll talk about now, solar prominences, solar flares, and coronal mass ejections, which in turn lead to our activity and auroras. So sunspots, let's talk about them. These are these dark spots that you see on the sun's surface, and they're a good indicator of the sun's general activity. They typically occur in pairs and groups. Pair here, here's a little pair here, pairs here, groups of them here. So they typically occur like that. That's what you get when you get look through a solar telescope. Just often if you see them out in the courtyard here or outside walk astronomy and someone's got one, have a look, and that's the sort of stuff that you see. Surface of the sun with these dark spots on it, and they're called sunspots. And just a close-up of a sunspot, I'm going to look aside on in 1 minute. That's what they look like. Those sort of darker spots there, they're still very, very hot, but it's just that they're cool. Why? It's because you've got these regions of concentrated magnetic field lines, these big loops, which I will see if I've got on the next diagram. I'm going to jump aside a bit. Here we go. So here what they are. Here is these twisted magnetic loops underneath here are poking up perpendicular because they're under so much stress and tension. Your magnetic field lines looping over like that, and you get this severe, quite a significant concentration magnetic field lines here and over the top, and that suppresses the uprising of that hot plasma, and that makes it, that whole area in here and here and in between them, let's go back now, it makes those areas a lot cooler to the surrounding surface. Because the surface here is about 5,800 and here still extremely hot. You're talking about 3,500 degrees, but it's just cooler in comparison to this, so it appears to be dark. And they're called sunspots, and that's what sunspots are. They're regions of concentrated magnetic fields that are coming up because of the tension and rising through the convective zone to the and arching over the photosphere. That's how big some of, there's the size of the Earth in comparison. So that's how big you're talking. Some of these large sunspots, individual ones, pairs and groups of them. They last anywhere between 1 and 100 days. The groups can appear together for up to about 50 days. And we've looked at that one there. Okay. Now, I mentioned there the sun goes through 11-year cycles. You may have heard of the terms solar maximum, solar minimum and stuff. And here along you've got the various dates along here on the x-axis. And here's the percentage of sunspots that are visible, or the sun's visibility here, how visible much of the sun is visible. And what this graph shows you that throughout the time of the solar activity as it approaches solar maximum, you get more sunspots and the sunspots tend to be larger. So more of them and they tend to be larger. So they correlate, there's a direct correlation between the sunspot numbers. They worked out that earlier, many, many years ago. They worked out the sunspot numbers, as they increase in size and numbers, you get increased solar radiation intensity and solar activity. And we now know why. This diagram I put in here shows a nice sort of image of the sun taking year by year by year from 1996, when the sun was relatively quiet at solar minimum, and here in 2006, and then we go through it right up to solar maximum in 2001, but you'll see how you're getting more and larger sunspots and groups and so on with solar activity. This is really solar activity which reflects as the sunspots, but you can see it's much more active at solar maximum.
Across your slide's got a typo.
I saw that, yeah, Bill. I saw that, yep. Spotted it, thank you. So here it is here. This is a nice little graph here too. Once again, solar activity. Every 11 years it goes up. Solar maximum, the last one was 2014, which means, yay, next year we hope to be in solar maximum. Okay, so sunspots. So you now know what sunspots are. You know what causes sunspots with the magnetic field lines, getting with differential rotation, twisting and distort them. They poke up, you're getting these concentrations, you're getting these sunspots. And I'm going to show you now how sunspots then evolve into solar prominences, solar flares, and coronal mass ejections. And it's these latter two that are responsible for sending charged particles our way and causing our lovely aurora. Now, solar prominences, yeah, these essentially big arched loops of hot plasma, clouds of hot plasma rising up here, and that's a big, there'll be a big loops in there of magnetic field lines, and the charged particles of the plasma are following those field lines. And you'll see there how the magnetic fields are anchored to the photosphere. They form over about a few hours to a day. They can last for hours and up to months. And they can expand right out and lose control of their plasma and become a coronal mass ejection, which we'll talk about, which refers to a large cloud. They can also expel a large cloud of material towards us as well. But look, there's the size of the Earth compared to that. Wow. This is another picture of during total solar eclipse, and there's the chromosphere which we looked at. There's the corona that we saw, chromosphere here, and here's some lovely big prominences. Picture of the Earth beside it, comparison. And that's, once again, I don't know if if you look through a telescope or a pair of binoculars at a total solar eclipse, that is what you see. You see the prominences, you see the chromosphere. It's just, and they are those colours. You see them with your eyes. They look beautiful. Okay, so those solar prominences. How about solar flares? Solar flares, and people often get the terms mixed up. Solar flares refers to sudden, violent bursts of intense light that you see on the surface of the sun. Very, very explosive. Here is one going off here, and it's just intense burst of solar magnetic activity and electromagnetic radiation, in other words, light, and that can go right through from radio waves, microwaves, infrareds, optical wavelengths, your ultraviolet, your X-ray to your gamma rays. It gets right across the spectrum. You see a big burst, and this is an X-ray image taken with an X-ray telescope. Sorry, actually, I think it's ultraviolet, actually. There's ultraviolet, that is. You can see it shooting off there. There it is, extreme ultraviolet. That means close to the X-ray part of the spectrum. We're going to talk about classes. It's important to know about what classes solar flares are. Okay, so what causes these sudden bursts of intense light and various wavelengths that you see on the surface of the sun? And it's all to do with these magnetic field lines here that arch up like that, and they get more and more stressed, more and more distorted, intense, and to the point of, if they happen to be near another one, they'll snap, they then separate, and then they reconnect, often with another set of lines nearby. And in that process, they become more stable, offload a lot of energy gets released as they become more stable and get rid of all that distortion going on. So here it is here, and all that energy acts to heat and accelerate gas within the corona to relativistic speeds, in other words, speeds up to the speed of light. So here it is here, you're getting these magnetic field lines, they snap, they open up, they come to a lower energy state. I'll show you a small video on that very shortly. And you get this release of light, and all that release of light and heat accelerates all the particles of plasma here, shoots them up to corona at velocities close to the speed of light. It's here. So that's a huge big flash here. It's a solar flare going off, and you're starting to get a big release of plasma being associated with it as well. Here's just a little video to visualize what I'm talking about when I say magnetic loop separation and reconnection. So here they are here, going in opposite direction. They're connecting, opening up, reconnecting, and they're in a more stable state, a state of lower energy. And that energy's got it, because they were before full of energy, all totally distorted and twisted up. They link up like that and release their energy and go into a lower energy state. Yeah, and I wrote that your magnetic lines reconfigure in a lower energy state, releasing energy to accelerate the particles that are around all the particles of plasma to produce that burst of light right across the spectrum and release those particles up into the atmosphere. So, how are solar flares rated? And we talked about that. So, solar flares are rated by their soft X-rays. As I mentioned, the solar flare will release light right across the entire spectrum of electromagnetic or light spectrum, right through from radio waves through to gamma rays. A lot of the photographs you see are all taken in ultraviolet. You know, I often see nice pictures like I showed before of the blue sun, and that's usually taken in ultraviolet. But they also have X-ray sense telescopes and observatories watching the sun very, very closely. And X-ray wavelengths you can split into two. Sort of the lower energy X-rays, you're talking still pretty powerful, but lower energy X-rays, they're called soft X-rays, and then the higher energy end of the spectrum within the X-ray class are called hard X-rays. But they look at soft X-rays in the channel between 0.1 and 0.8 nanometer, or 1 to 8 angstroms, depending how you think of it. That's the wavelength of light they look at. So they look at the flux or the strength of the light that gets emitted in these wavelengths here. And from there, they decide the class B, C, M, or X, increased by a factor of 10, so that's exponential, pretty much like the Richter scale, how they grade earthquakes on Earth, pretty much the same. And then within each class, there are subclasses 1 to 9, 2 being twice as powerful as 1, and 3 being 3 times as powerful and so on. Except for X, there's no limits. You can just go X 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You can just keep going on the X. That just keeps going up. So here it is here. So 1 is 10 times the strength. So rather an X class here is 10 times the strength of an M1, and an X3 is 3 times the strength of an X1. So that illustrates that. I'll put here. So you've got to know about that now, because the news reports this. You know, it's been reported on the news now. Oh, we expect some aura. We've had an X class 5.8 flare, and one of your friends will probably ask you, "Hey, what does all that mean? Why do you?" And it means you've got to impress your friends. You've got to know about this. And you say, "Well, I know what that means. It's about the soft X-rays between 0.1 and 0.8 nanometer." And here's a nice tracing just over a time period on December the 14th from one of these X-ray satellites. And forget the blue. This is the red is the channel 0.1 to 0.8 nanometers. And you can see here that here's the flares, and they've graded them accordingly to their flux. This was an M5.8, an M2.3. This one was a lot higher, so it was in the X class area, and it was a 2.8. So next time when you see those in the news, you immediately know what they're referring to. It's referring to the flux from the soft or the lower end of the X-rays. Okay, now what can happen then is a solar flare itself doesn't cause a lot of harm to Earth. That intense electromagnetic radiation, X-rays, they can go to the Earth and cause some very temporary radio blackouts on radio wavelengths, but usually no major big disruption, but it can cause that sort of disruption. The important thing is what happens with these more powerful solar flares is that as they release that energy, they can release a heck of a lot of solar plasma material, causing what we call a coronal mass ejection. And it's these coronal mass ejections, not the solar flares, that cause the aura, that causes the upset to all our technology and so on that you hear about, the concerns. So let's talk about them. So they are an extreme release of plasma from the solar corona as the magnetic loops open up, snap and open up and reconfigure themselves, and all that energy gets released and throws them out. So the flare is only the instigator of them. Now these coronal mass ejections can occur from a solar flare typically. They can occur just on their own. You can have a quiet patch of the sun with some sunspots, and suddenly you get a big burst of activity without having a solar flare, and just a big pile of plasma goes out, or one of those prominences can give rise to them as well. But typically it's a solar flare, and of course the more powerful the solar flare, the more likely you are to get a coronal mass ejection, and all this material starts heading our way. To give you an idea of these CMEs, they call them, it's solar minimum, one about every 5 days, but solar maximum you get several per day. And they can be anywhere 15 to 5 days to reach Earth. You're getting billions of tons of material that get lifted off the surface of the sun, accelerated speeds up to about 3,000 kilometers per second. And this is where they've put what they call a coronagram over the telescope, just a big disc, so you block out the glare of the sun, so you can see all the activity out here in the corona. Look at these big chunks of plasma getting biffed out. It speeds up to 3,000 kilometers per second. Pretty amazing. So that's a coronal mass ejection, and it's these events, often triggered by a solar flare, that heads our way and causes us sometimes some chaos, but certainly our beautiful aura. Now this is just a short 30-second video showing this of some solar activity.
Battery 100%.
There's a picture of Earth comes up here. Give you an idea. But these are big loops of magnetic field lines. This is all hot plasma. There's Earth, in comparison to the size of it. They call this coronal rain, because it's just raining on down. So that 30 seconds, that happened over about 3 hours in real time, to give you an idea. So that's the sun and the solar activity. So now you know the internal goings on, the anatomy inside the sun, you know the physiology of how things are working, how those magnetic field lines get generated and get twisted and distorted, raise plasma up, and then they try to reconfigure themselves to a lower energy state and just in the process release huge amounts of energy and hot plasma sending towards Earth. So let's talk about Earth's magnetic fields and the aurora. So key to Earth, one of the things that protects life on Earth is these big magnetic fields called a global magnetosphere. It's because we have a molten iron in the core of the Earth, and as it gets sloshed around and rotates and goes through some convection movements as well, it generates these magnetic field lines. There's what we call a dipole, because you've got this is a north magnetic pole here and a south magnetic pole here, but you can see these lovely big magnetic field lines, and that protects us constantly. As I mentioned before, you've got that constant low flux solar wind going on, and if that solar wind gets trapped by our magnetosphere and deflected away from us and protects our atmosphere. And that's why Mars does not have much of an atmosphere, because it lost its magnetosphere and the solar wind just quietly eroded its atmosphere away. So we're very grateful for that global magnetosphere. And what happens, it protects us from these big coronal mass ejections as well. And let's go and have a closer look here. So when this is part here is when these charged particles do get trapped and enter Earth's atmosphere, they start exciting molecules in the atmosphere. And there's two principles. One is the atoms just in the atmosphere just get excited, and that's where here's the nucleus of an atom. Here's electrons, and there's showers of electrons here at discrete energy levels. And here's a high energy photon or a particle comes along, interacts with this electron and excites it and bumps it up to a higher energy state. But eventually it wants to fall back to its lower energy ground state, and when it does, it emits a photon of light, also known as fluorescing. And that's why excited atoms emit light. And typically in the context of aurora, high in the atmosphere, you're talking sort of between 250 up to 800 kilometers up. It's typically oxygen that gets excited by these charged particles and high energy photons, and that typically emits green or sometimes red, depending on the latitude, or rather the altitude you're talking rather, and the particular energy state at which that electron concerned was bumping up from and then coming back to. And then there's the principle of ionization, where you're not just bumping an electron up to another excited state, you're actually booting the electron completely away from the power of its nucleus, the attraction of its nucleus there. So it gets completely booted off, and that's called ionization, that process. In the context of aurora, that typically involves nitrogen that gets an electron by one of these charged particles. It boots an electron right off the atom completely, but the electron then comes back again and emits light in the process. And with nitrogen, it's typically a blue color, or sometimes, depending on various energy levels and its altitude, then it's purple. So that's what's happening between the charged particles and the oxygen and the nitrogen. Now, so there's four stages of creating the aurora. So let's look at the first stage first. Solar wind has been released, and this is going to create the daytime aurora. It's starting to connect with the magnetic field lines, get directed down towards the poles, and you get your daytime aurora when you see aurora lights at the polar regions in the daytime. Stage 2. Creates the night aurora, and you'll see the solar wind starts directing, and like a flag almost flapping in the wind, it directs the magnetic field lines backwards like that. Here is your charged particles coming back like that as the magnetic field lines are all being pushed. So that's stage 2, and then stage 3 is these magnetic field lines. They sense one another. They want to reconnect, magnetic reconnection. They hook up, and these charged particles have got nowhere else to go but follow the magnetic field lines towards the poles, and you get your nighttime aurora. So those are the stages what happens to the magnetic field lines to create the daytime and the nighttime aurora. Now you've probably heard all these different lights and stuff. You can get different hues and tones of lights and colours and so on. Two main colours are sort of a red, violet, pinky and a green sort of hue. And it all comes down to what atoms are getting excited or ionised and to what degree and at what altitudes. And let's have a look. So first up, between about 250 kilometres to about 800 kilometres upward, it's predominantly oxygen that's glowing, and that causes the red colour, and you also get a little bit of mixing with a little bit of nitrogen as well, and you get this sort of violet colour up here. Moving down to altitudes of about 100 to 250 kilometres, you get predominantly it's nitrogen that's getting fully ionised, and you get a little bit of less, but you get a little bit of oxygen up there, just mixing in with it, a bit of oxygen getting excited, and that creates this lime green sort of hue here. And then if you go down to about 75 up to about 100 kilometres, that's where you start getting, there's less oxygen there, but you're getting, that gets excited, but you're getting nitrogen ionised. And remember, that means booting the electron off, and that electron there is usually got enough energy where it excites another nitrogen to create a pink sort of a pink colour there. So red and blue gives the pink colour combined, and you get that there. So that explains why you get these layers of different colours. The bottom line it comes down to is whether it's an oxygen or nitrogen, at what altitude, and to what degree is it excited or ionised. So the particles then follow down towards the magnetic poles, and you start getting what we call these auroral oval zones here. And because we're constantly getting auroras from the solar wind, we just get excited about it when we start getting these geomagnetic storms, when these big coronal mass ejections sends large amounts of particles our way. So this is where you get your standard auroras here. This is the north geomagnetic pole and the south one here. So these are called the aurora borealis and the aurora australis here. Now, you always hear people talk about the northern lights. You don't get a lot of people talk about the southern lights, the northern lights this, the northern lights that. And the only reason is they're both equal on both poles. It's just that the northern pole, or the northern hemisphere, it's more populated and the area is more accessible. So you're looking at all these countries. You're looking at the top bits of Scandinavia, Europe, Canada, parts of the States and so on, as opposed to, look, it's a bit of the Antarctica. Otherwise, it's predominantly all ocean. A little bit of Stewart Island in the bottom part of the South Island. But for your basic aurora, that auroral oval really is just over ocean, most of it. But it's not to say it's of any less, by no means. So when we get these big coronal mass ejections that are usually triggered by these big X-class solar flares, that you get these geomagnetic storms. And we had a G5 last month. That's what we saw way down here, so you see it extended. And I did see somewhere on a map for the southern hemisphere, but we saw it here. Yeah, it went through most of New Zealand, which was quite cool. In case you're wondering, the KP index just is a measure of the disturbance of the magnetic fields in general, so you don't really need to worry about that. But it's the G1, G2, G3, G4 and G5, the strength of geomagnetic storms, that the media usually publishes along with the size of the flare. So this is the sort of stuff that you now know. So the G5 gets really down at these lower latitudes. Really, really good site, www.spaceweather.com. Fantastic site, explains all of this, plus it gives you daily updates, what's happening on the sun, what sort of grades, classes are the solar flares going on at the moment, are they directed towards us or not, what sort of geostorms they're expecting. It's just fascinating stuff. It's a great read, and yes, you can plug New Zealand into it too. Okay, so yeah, geomagnetic storms, the G1 to G5, as we've alluded to, that's a disturbance of the whole magnetosphere where it really, really gets disturbed. And of course, the fun part of it gives us these auroras, these lovely light shows. But with modern society, we rely on power grids, we rely on electronics and technology, satellites, communications, aeroplanes, and so on. And they've got a huge potential to cause trouble from there. So that's why the importance of space weather is learning how to predict these coronal mass ejections, know what's coming up, give people warning so they can start shutting some things down or putting them into safe modes and so on. And that's the whole point of it, really. Now, I've just got a quick 3-minute video that just brings all this together really nicely. So let's, that's the speakers on. Just the whole lot, what I've said in the last 50 minutes into 3 minutes. She says, why didn't you just shut up and just put the video on? I could have, but it wouldn't have been as fun.
On Arctic nights, the aurora often flames across the winter sky. What is it, and where does it come from? This is where the tale of the aurora starts. On the Sun, a star of average size among billions of other stars in our Milky Way. The Sun acts as an enormous power plant. The energy is created deep inside the core of the Sun. Here the temperature is over 14 million degrees, and the pressure so enormous that hydrogen atoms are squeezed together into another element, helium. This nuclear reaction releases energy. The light radiates outward from the core of the Sun. In the outer layers, the heat moves to the surface in huge eddies called convection cells. These electrical currents of charged gas create magnetic fields inside the Sun. In some places, strong magnetic fields push their way up through the surface. They slow down the eddies of hot gas. The surface cools, and darker sunspots appear. The electrically charged gas is called plasma. The plasma drags the magnetic field further outwards. The magnetic field stretches and twists like a rubber band, and then the rubber band breaks. Several billion tons of plasma is hurled out from the Sun. This is called a solar storm. The solar storm can reach speeds over 8 million kilometers an hour. After 6 hours, it blows past the planet Mercury. After 12 hours, the planet Venus. When the solar storm reaches our planet, something strange happens. An invisible shield, the Earth's magnetic field, deflects the storm. The magnetic fields couple together and create a funnel where the gas streams down on the daylight side of the pole. This is the daylight aurora. The magnetic fields stretch further back and couple together. The magnetic rubber band breaks, and gas from the solar storm streams along the magnetic lines towards the poles on the night side. This is the nighttime aurora.
Are usually your nitrogen. Yeah, so that sort of brings it together quite nicely, that quick video. And I'll put this one here for some of you might be interested into the research that's going on. I've just scratched the surface about these loops of magnetic fields and the snapping open and the magnetic reconnection and how plasma forms to create these coronal mass ejections. There's just constant research going on, and this typifies it very nicely, just some of the research going on, because they're constantly trying to work out what's going on so they can predict these events as we get more and more reliant on electronics and satellites and communication networks and so on. So here's just a very short video to illustrate that.
Coronal mass ejections, or CMEs, are huge clouds of plasma and magnetic field occasionally thrown off by the sun. Scientists study them because the massive bursts pose a threat to space-based technology and even power grids on the ground. Within each CME lies a kernel known as a flux rope, tightly wound groups of magnetic field lines that can contain and transport solar material. Astronomers have seen them as the CME bursts off the sun, but they have been next to impossible to detect on the sun itself. New research using NASA's Solar Dynamics Observatory has now shown that they can be seen in just one of its cameras, which shows the very hottest material on the sun. By watching a flux rope form and eject as a CME, the research has brought some closure to one long-standing mystery, whether ropes form before or during the CME's eruption. It's impossible to actually see the flux ropes, or any of the sun's powerful magnetic fields involved with CMEs and flares, because these fields are invisible. But scientists can map them by observing plasma trapped by these fields, which shows up as thin lines of extreme ultraviolet light. Since Earth's atmosphere naturally filters this UV light, scientists must observe it using telescopes in space, such as NASA's SDO, so there have been relatively few detailed observations of CMEs, particularly at higher temperatures. SDO images the sun at high image and time resolution. It is also the first satellite to consistently observe light with a wavelength of 131 angstroms, which highlights plasma at temperatures of around 10 million degrees. This wavelength is usually reserved for studying solar flares, but what NASA and Naval Research Laboratory scientists found is that the flux ropes associated with CMEs could only be seen at this temperature. On July 19, 2012, a CME erupted from the visible edge, or limb, of the sun. Because it was on the limb, the flux ropes were in profile and particularly visible. Even more important, the flux ropes appeared about 7 hours earlier in the same location. The ropes were visible as a line of figure eights that looked exactly the way theorists predicted they would. This is the first direct evidence that flux ropes form well before coronal mass ejection. Footage of the CME from the SOHO spacecraft confirmed the presence of the flux ropes. By adding footage from the Stereo A spacecraft, which is viewing the sun from an entirely different angle, the researchers were able to create a three-dimensional picture of the flux ropes. For the most part, they follow the classic figure eight pattern previously observed and predicted by solar models. But some of these ropes also had feet which extended farther away than scientists expected. This deviation from the models is interesting and requires further study. Besides showing proof of early flux rope formation, this study also paves the way for future flux rope and CME research by literally finding a new light to observe them in. The possibility of using flux rope formation as an early warning system for CMEs means that this line of research can have some very practical and far-reaching applications. And it can also help wrap up some of the long-standing mysteries of the sun.
Yes, I hope that's giving you a bit of insight into the depth of research that's going on, and they're trying to work out what event happens, how the magnetic loops, what happens to them, how do they behave before a coronal mass ejection, because those coronal mass ejectors that we want to know about. So it just gives you some insight into that. These are 3 frequently asked questions, which we'll look at now. What caused this current display, looking at through the Aura's eyes versus the camera and other planets. So, what was responsible for last month's Aura? And the bottom line is it was a sunspot. They're all labelled. AR stands for active region, 3664, and it was over this sort of region here. It was a whole group of sunspots with multiple flares going on. But it was caused by an X5.8 class, which you now know. Wow, that's right up there. That's very powerful, because you think, yep, I know what that means. Class solar flare that evolved into a coronal mass ejection, which most flares at that sort of power, at an X class of 5.8, that's usually would almost certainly give you a coronal mass ejection at the time. So it was that coupled with it was just happened to be directed towards the Earth at that time, as opposed to here or shooting off in any other direction. And that's what's caused the auroras last month, that weekend, that Saturday night. It was gorgeous. This here is actually an ultraviolet wavelengths. Here there is ultraviolet wavelengths. So later, a few days later, it actually sent off a more powerful one, an X8.7 flare, but fortunately it was not aligned with Earth. The one that was aligned with Earth was over about here. The sun had rotated around, it was about 3 days later, and here it is here just as it disappears around the western limb of the sun. So it wasn't aligned with us, but that was a much bigger flare again. Now, coming up, it's actually been around the far side of the sun. It's coming back into view again, and it's been renamed now, Active Region 13697. So that's the one to look out for. It came back into view just on the 30th of May. That was what, Thursday, wasn't it? Yeah. And it was very active, giving out plenty of X-class flares. So very, very powerful. Will we get more aurora this far up in Auckland? We don't know, but the best chance, we're the 3rd of June now, the 4th through the 6th of June, is they're predicting when it will be, that sunspot region will be aligned with Earth, and it will throw some powerful solar flares and subsequent coronal mass ejection. We could be in for another geomagnetic solar storm. We don't know yet, we've got to wait and see. So let's hope we have clear nights essentially over this week. We're due for it this week, if it happens. Okay, yeah, so often you see these amazing pictures of these colourful lights, but you don't see them with your eyes. We were so lucky in Auckland. You could see all those colours yourself. You didn't need a camera. But the reason why we don't see colours very well at night is in the back of our eyes and the retina, we have a series of cones and rods. The rods are designed for looking at black and white. They're very sensitive in dark situations. The cones detect colour and they're not very sensitive in the dark. They respond more in bright lights. So at night time, our cones aren't very good at picking up colours, but our rods are very good at picking up black and white contrast. So as opposed to a camera, all its detectors have got equal sensitivity day or night, and of course you've got the option to have long exposures as well. So that's why the camera will pick up a lot more detailed pictures than you see with your eyes. Another one, yeah, do other planets have aurora? Absolutely. All the 2 gas giants and the 2 ice giants further out, so Jupiter, Saturn, Uranus and Neptune, they all have magnetospheres. So absolutely, they all get solar wind goes out that far, these coronal mass ejections can go out that far, absolutely. So here's a lovely image from the Hubble telescope of Jupiter's aurora. It's North Pole. Okay, so that's what happens inside the sun, how it causes these solar activities and how it influences Earth, how it interacts with our oxygen and nitrogen high in the atmosphere. Let's just wrap up. Okay, so the sun generates magnetic field lines, vertical ones, that get twisted and distorted due to differential rotation, which is all because of the fluid behaviour of that less dense outer convection layer. Those distorted magnetic lines that get twisted up like a rubber band, go up perpendicular into loops and punch through the photosphere, carrying plasma with them. These then suppress the magnetic activity, suppress the plasma down below them, create these darker sunspots. And the sunspots are very indicative of solar activity in general, which of course the sun goes through 11-year cycles. The intense activity from the sunspots, the magnetic fields that are associated with those sunspots results in solar prominences, solar flares, and those coronal mass ejections. It's Earth's global magnetosphere that deflects the charged particles towards the poles when they come our way, whether it be solar wind or whether it be in a geomagnetic storm in the context of a coronal mass ejection. And it's the solar particles that interact with the oxygen, in particular oxygen and nitrogen, and depending on the two and the energy that was involved and the altitudes, that cause the aurora of different colours. So summary in short, you get charged particles from the sun travel along Earth's magnetic lines to interact with oxygen and nitrogen in the upper atmosphere, causing those gases to glow. That's sort of in a one sentence nutshell. So, next time you see a picture like this in Aurora, I want you thinking this. What's going on in the sun's surface? And that's the sun and the southern lights. What's going on? Thank you very much. Are there any questions? Yeah, cause I've got one that I always keep a second set of slides. I'm aware of time. It actually was bang on 60 minutes. I always keep a second set of slides up that I've taken out, so I don't want to muddy the waters at the time, or someone asks a question. But since there's no question, I'll just show you one or two, because a question that came up when I gave this talk the other day in a group was, why 11 years? How does the sun reset itself? You've talked about how it gets twisted and distorted. And why the cycles? I've got a good question. So I've prepared some slides. Protect your eyes. So let's look at some of the outtakes. We've got a little bit of time. We've got time, haven't we, guys? Yeah. Oh, coronal holes. That's another thing you often get that I purposely took out. But they sometimes can give rise to coronal mass ejections. Essentially, that's where you get magnetic field lines that haven't reconnected. They're just open, and charged particles are not being suppressed and allowed to fly out. Okay, so this is all part of the story of why the sun goes through these 11-year cycles. What's the nuts and bolts of that? And the bottom line is that this is a famous diagram called the butterfly diagram. And the bottom line is, as the sun goes from solar minimum through to solar maximum, sunspots tend to start popping up and moving more and more to equatorial latitudes. And you can see it here. They've just done the positions here, the latitudes of this equator here up to the poles, and there's the latitudes here, and they've plotted the number of sunspots with each year. And you can see, if you look up a line, here's obviously a solar maximum. Here is a line here with solar maximum. There's your lines there. But notice afterwards, or just leading into it, I should say, as they get more and more towards the equatorial latitudes. And what happens then is, the other little thing to mention is that, as I said, that these loops, these sunspots, often occur in pairs. We've got these magnetic loops. You've always got a north pole, which is the direction which charged particles will go from north to south. And in one hemisphere, let's just call this the northern hemisphere, it doesn't really matter, but one hemisphere, all the sunspots in pairs are arranged whereby in this particular one, it's the leading sunspot, it's got a south magnetic pole, and the following one lagging it, it's got a north. The other hemisphere is the opposite. The sunspots in pairs, the leading one will be the other one, which in this case is north, and the one behind it is south and here. And as it approaches solar maximum, the sunspots move more and more towards equatorial latitudes, like here. And suddenly you start getting, here we go, and you start getting, this is obviously, they've made this very gross so you can see it, but it's on a smaller detail and brought together. This is just for the diagram purposes. But you can imagine these pairs getting closer and closer together. Suddenly the two leading ones, the south here and the north one here, these loops join up and then reconnect. And up here you started with north at the top, the north magnetic pole, south down here. Here getting distorted. Here's your nice little pairs. They get more and more towards the equatorial latitudes. And notice that because this one here, the south one was leading here, and it's joined up with the north one leading here, and suddenly you get a whole big stack of those all lining up together. Suddenly the pole changes as well. Not only have you cancelled all that activity out and you've reset the activity level again, but you've actually reversed the polarity of the sun. So the sun actually goes through two cycles. It goes through 11-year cycles between solar maximum and solar minimum, being really super active to being really quiet, but also it goes through a 22-year cycle of every alternative time. It completely flips its magnetic pole. So that sort of nice little diagram explains why that happens. And here's, that's the same diagram here. I think I've done some lines. Okay, your solar flare, which is these. So this is how they work out the solar flares. I said they're not like your coronal mass ejections where you're getting particles that are upsetting geomagnetic storms and upsetting satellites and planes. But the solar flares themselves are big blasts of X-ray and ultraviolet light and stuff, and they are classed as well along with the, according to how great it was at the wavelengths of soft X-rays. But what can the flare itself do? Because people often get mixed up. Oh, the solar flare affected us. They've got things a little bit mixed up. So it was the coronal mass ejection that actually caused the chaos on Earth, which was triggered probably by the solar flare. The solar flare itself, yes, it can cause some trouble with some brief radio blackouts, and really a more serious an X-ray solar flare. Just the X-rays itself coming away can trigger some radio blackouts throughout. Most of them are usually M-class and cause some brief blackouts in the polar regions. So that was just, I think that was it. Oh, okay, one question I had here, and I gave a talk on the sun about 3 years ago. Someone asked the question, how strong is the sun's magnetic field? And so the Tesla is what they use, the unit that they use, and here is Earth sitting up here, 0.005 Tesla. The sun's magnetic field, you think it'd be so much more powerful, it's twice as powerful. But of course, it extends for huge, huge distances right up to the outer aspects of the solar system. Here's your fridge magnet, and think, gosh, I thought that would be very weak. But imagine if the sun was that strong, we'd be in great trouble. Here's your sunspots. Yeah, junkyard magnet is 1 Tesla, an MRI scan in the hospital. That's why the hospital says, do not take anything metal into that room. Thank you very, very much. Or if you've got a metal prosthesis, you can never have an MRI for that exact reason. So that's another little interesting thing. Oh, the sunspots, the magnetic strengths over there, that's suppressing the plasma coming up. That's the magnetic strength is about 4,000 times than at the poles of the sun. Yeah, and that's it, gets complex. Here's all your hard X-rays. They all come from this, where your particles are crashing down on the surface of the sun, giving way to hard X-rays. But it's your soft X-rays up here that they find it easier to observe and to record the flux, the strength of, and grade their solar flares according to that. So I think there's any other questions around that? Otherwise, yeah.
I've got 2, please.
Yeah, 2.
The particles that are coming to Earth from the sun, are they generally plasma particles?
Yes, charged particles from the plasma of the sun. Electrons, protons, or alpha particles. A little bit of heavier elements, but predominant electrons and protons with about 2% helium nuclei.
Okay, and my second question is, I've recently got into amateur radio, and you use the atmosphere to bounce off
the
radio
ionosphere,
wave, just to bounce off and come round to the other side of the Earth, so you can transmit right around the Earth. And not long into it, but supposedly it gets better, the transmission ability, when you're getting closer to solar maximum. Why do you think that would be? Oh,
because solar maximum, you've got more solar flares going off and stronger solar flares, and it's the high grade is those high energy X-rays and extreme ultraviolet, in particular extreme ultraviolet, and those soft X-ray photons of light. So it's not charged particles this time. They're from the CMEs. This time the flares give off the photons. And it's the X-rays and those extreme ultraviolet wavelength photons that are going into and disturbing the ionosphere, which upsets your radio communications.
It improves it. During a solar burst, it's bad.
Yes.
But generally, you get a better transmission.
Yes, I have heard that actually. Yeah, and someone said they could hear so much further; they could almost hear right around the world. And that it disturbs I'm unsure of all the science of it, but it disturbs and alters the ionosphere. So that's from the photons from the actual solar flare that's doing that versus the CME, which causes the aurora. And often, and it's worthwhile getting that right here, because so many people talk about, the solar flares just sent all these particles. No. The solar flare was the underlying process, but it created a CME, coronal mass ejection, which then caused that. The solar flare just refers to that short, intense burst of light
Yes.
Photons, yeah, which then affects your ionosphere, which then can have an effect, whether it be positive or negative, on your ham radio. But you get those radio blackouts at the polar regions. Yeah.
Interesting.
Yep.
Thank you.
Bill?
I was just going to say, there's quite a big variation in the strength of each solar cycle. Obviously, your chart showed a couple of cycles ago there was a particularly strong one. Is there any good theories as to why that variation from cycle to cycle?
No, I think that is just with nature, the variation of nature. I did look up why 11 years. We know, okay, I've explained now the cycle, why we get solar maximum minimum, and yes, Bill says solar max is just, the graph is not like that. You might get a really great year, a great solar maximum, and then the next solar maximum 11 years later might be a little bit of a fizzer, so to speak. It's more active, but not as active as that one. So you learn that in biology whenever you plot graphs. Engineering is all dealing with straight lines. Biology is just that, or nature. Is why 11 years? Is there any secret behind 11 years? Just the way it is, and it's probably just due to just the way it turned out from the sun's fossil magnetic field lines. In other words, when the sun was very fast forming, just how it's certainly velocity, its rotation rate, how thick it was, how much material was going on, those very first what they call fossil magnetic field lines. That whole process dictated that our sun resets itself, because someone asked, why does it reset itself every 11 years? Why not every 12 or 13? And it probably relates to when the sun first formed with those fossil magnetic field lines. But at least you now understand why, or rather how it resets itself every 11 years, and how there's also a 20-year cycle where the sun flips itself over in magnetic poles.
It's probably a function of the differential rotation. If the difference was slower, then it might be 100-year.
Yeah, in the rotation, which all to do once again with those with how the sun formed and the rotation rates and so on. Yeah, absolutely. Yep. Yeah.
You should be able to observe these in some other stars as well, solar cycles these days.
Yeah. Well, the helioseismology, that's a whole field. They, never mind studying the sun. It's important to study the sun. It's important to us. It's our closest star. Study it well. But even from distant stars, they study the isolations on the surface of it. It's a whole field of science, and that's how they work out the interiors of all those other stars around us. You think they're so small in the sky, but the equipment is so sensitive. They can study all the little pulsations and actually work out the interior of distant stars just by studying the pulsations of it. Yeah, it's fascinating stuff. Do you have a question here down the back?
In terms of the sun, the speed, the differential speed you were talking about, how it changes at the equator as opposed to the poles.
Yes.
It would seem the other way around, like you would think that it would be faster nearer the poles rather than faster at the equator. You were talking about the liquid moving around.
Yes.
Right? Yeah, it just seems illogical.
I think a lot of it's to do, because it is a liquid, there's a lot of forces in play there, and even right down to centrifugal forces going on as well, where in your plane of the rotation, things do travel, things are going to be experiencing higher velocities. I know what you're saying, like for example, in a uniform thing like the Earth, someone sitting on the surface of the Earth, they are travelling at a slightly different velocity to someone at the equator and so on, but the whole thing is rotating uniform. But it just so happens there's multiple factors in there whereby just the laws of physics says no, things, the surface of the sun, those outer layers, are rotating around at a faster velocity. Yeah. And how you might say, how do they know how fast the sun's rotating? Because there's no landmarks like mountains and stuff on it. Sunspots, they study the sunspots and watch them move around. And it's something they've just worked out over the years. But yeah, good question. Otherwise, we're all good? Yeah. Okay, guys, thank you very, very much, and drive home safely. Thank you.